All right, let's get into it and set up a PostgreSQL database on Kubernetes. You probably already know Kubernetes is a powerful tool for container orchestration. But today, we'll break it down step by step like a cookbook guiding you through setting up Postgres on your Kubernetes cluster, ready for your applications to connect to it.
Sounds delicious. And what better place to start than with config maps, the heart of configuration management in Kubernetes?
Okay, so config maps.
Uh,
They sound kind of important. What exactly are they and why do we need them?
Imagine you're baking a cake. You wouldn't mix all the ingredients directly into the batter, right? You'd have separate doughs for your flour, sugar, and eggs, each with their own specific measurements. Config maps work similarly in Kubernetes. They act as containers for your application's configuration settings, keeping them separate from your code.
So instead of hard coding values like database names.usernames and passwords into our application, we can store them in a config map and reference them from our code. Got it. But how do we create a config map? Let's see some code in action.
Absolutely. Let's create a YAML file called postgres-configmap.yaml to store our PostgreSQL database settings.
Okay, postgres-configmap.yaml. What goes in there?
First, we'll define the Kubernetes API version and the kind of resource we're creating, which is a config map. Then we'll give it a name. Let's say Postgres config for clarity, finally. We'll add the data section where we define our database settings as key value pairs.
All right, so it's a simple structure. But what about specific settings like the database name.username.password? What would that look like in the YAML file?
For instance, to set the database name to myb, you'd add a line like postgresed myd in the data section. Similarly, for the username, you'd use postgresuser.myuser, and for the password, postgrespassword.mypassword.
Got it. So we've defined our config map. How do we actually use it in our Kubernetes cluster?
Simple. We apply it to our cluster using the kubectl apply-postgres-configmap.yaml command. This tells Kubernetes to create a config map based on the specifications in our YAML file. To verify, you can use kubectl get config maps. You should see Postgres config listed there.
Perfect. Now we have our database settings nicely organized and stored in a config map. But what about the actual data? Where does that live in a Kubernetes environment?
Excellent question. That's where persistent volumes and persistent volume claims, or PVs and PVCs for short, come into play. They're the dynamic duo that ensures your data survives even if your pods are restarted or rescheduled.
Wait, pods restarting. Why would that happen? And why would my data disappear?
Pods in Kubernetes are designed to be ephemeral. They can be created, destroyed, and rescheduled across different nodes in the cluster for various reasons, like scaling or node failures. Imagine if your database pod suddenly disappears and your data vanishes with it. That would be catastrophic.
Okay, I'm starting to see why persistent storage is so important. But I'm still a bit fuzzy on how PVs and PVCs work together. Can you elaborate?
Think of it like this. A persistent volume is like a hard drive offered by your cloud provider or your own infrastructure. It represents raw storage capacity available in the cluster. A persistent volume claim is like a request for a specific portion of that hard drive with specific access modes and storage capacity.
So it's like saying, hey, Kubernetes, I need a 10 GB slice of that persistent volume for my PostgreSQL data. Kubernetes says, sure, here's your claim ticket.
Exactly. And that claim ticket is your persistent volume claim. It links your application, in this case PostgreSQL, to a specific portion of storage that persists even if the pod is terminated.
Okay, I'm flying. But how do we actually create these PVs in PVCs? More YAML files.
You bet. We'll need two YAML files, one for the PV and one for the PVC. Let's call them postgres-pv.yaml and postgres-pvc.yaml respectively. In the PV YAML file, we'll define things like the storage capacity.access modes and the type of storage, such as a cloud-managed disk or a local directory on a node.
What of the PVC file?
The PVC file references the PV by name and specifies the desired storage capacity and access modes. It basically says, I want this much storage with these access permissions from this specific PV.
All right, let's dive into some code. What would a basic example of a PV YAML file look like?
Let's say you want to use a local directory on your Kubernetes node for persistent storage. For this example, your postgres-pv.yaml would look something like this.
YAML.
v1, persistent volume.name. Postgres-pv.capacity.storage, 10gi.access modes, read write once, persistent volume reclaim policy, retained not hostpath.path.data Postgres.
Okay, we've got abby version.kind metadata with a name. Looks familiar from the config map file. But what about spec? That seems to have a lot going on.
Right. Spec is where we define the specifics of our persistent volume, in this case. We're setting the storage capacity to 10 gigabytes using storage. 10 GI.
And what about access modes? What's read write once?
Access modes defines how the volume can be accessed. Read-write once means the volume can be mounted as read-write by a single node at a time. There are other options like read-only many for read-only access by multiple nodes and read-write many for read-write access by multiple nodes.
So we choose the access mode that suits our needs. What about persistent volume reclaim policy?
This defines what happens to the volume when it's released from a claim. Retain means the volume will be kept but not automatically reused.
Interesting. And finally, host path. That seems pretty self-explanatory. It's the path on the host where the volume's located.
Exactly. We're using data Postgres in this example, but you can adjust that based on your setup. Now onto the PVC. Postgres-pvc.yaml.
Great. Let's see how we request a piece of that persistent storage pie for our PostgreSQL data.
Here's a simple example for Postgres-pvc.yaml. Postgres persistent volume claim name. Postgres-pvc. Access modes. Access modes read write once. Resources.request. Storage. 10GI. Storage class name. Then
Okay, so we have the usual suspects, apaversion.kind and metadata with a name, and then spec again. It seems like access modes needs to match what we defined in the PV.
you got it. We're using read write once here to be consistent with our PV.
Then we have resources with requests for storage. Again, 10GE to match the PV. But what's storage class name? Is that like a label or something?
Storage class name is how we connect our PVC to a specific PV. Manual, in this case, indicates that we're manually provisioning the storage, meaning Kubernetes won't automatically provision storage for us.
All right, so we've defined both our PV and PVC. How do we actually make them live in the cluster?
Just like with the config map, we use kubectl-apply. So it's kubectl-apply-f postgres-pv.yaml, and then kubectl-apply-f postgres-pvc.yaml, and voila, you have your persistent storage set up.
Perfect. So now we have our configuration sorted with config maps and our data storage handled with persistent volumes and persistent volume claims. I feel like we're getting closer to actually launching PostgreSQL itself. But before we get to that, let's take a quick recap. We started with config maps as the containers for our application settings, separated them from our code. Then we moved on to persistent volumes and claims, which are crucial for ensuring that our data survives the ephemeral nature of pods in Kubernetes. We're making great progress.
Absolutely. We've laid a solid foundation. Now we can get to the exciting part, deploying PostgreSQL itself. But we'll save that for the next part of our deep dive.
Sounds good. I'm eager to learn how to actually bring PostgreSQL to life in our Kubernetes cluster. So stay tuned, folks, for the next installment of the deep dive. Welcome back. Last time we covered config maps for managing settings and persistent volumes with persistent volume claims for ensuring our data sticks around. Now let's get PostgreSQL running in our Kubernetes cluster.
Right. We need to create a deployment to manage the life cycle of our PostgreSQL pods. It's like a blueprint that tells Kubernetes how to create and manage the pods running our database.
So just like with config maps and persistent volumes, we'll define this deployment in a YAML file. All right, what should we name this file?
Let's call it postgres-deployment.yaml. In this file, we'll specify everything Kubernetes needs to know about our PostgreSQL deployment, including the container image we'll use, the number of replicas, and how it connects to our persistent storage.
Okay. I'm ready to dive into the YAML. Give me an example of what that would look like.
All right. Here's a basic postgres-deployment.yaml file.
YAML.
Deployment.name, postgres-deployment.replicas, oneselector.matchlabels.app.postgres.template.metadata.app.postgres.spec.containers.name.postgres.image, postgres.14 ports, container port 5432, nbfrom.configmapref.name, postgres-config, volumemounts.name, postgres-datanonpep.masterbarthed, volumes.name.postgresdata.postgresdata, persistent volume claim.claim name, postgres-pbc.
Whoa, that's more complex than our previous YAML files. Let's break it down piece by piece. We have the familiar API version, kind, and metadata with a name. Then there's spec again. But it seems much more involved this time.
Right. Spec is where we define the deployment specifics. First, replicas. One tells Kubernetes we want one instance of our PostgreSQL pod running. You can increase this for high availability.
So if my pod crashes, another one will automatically spin up to take its place.
Exactly. Kubernetes will always strive to maintain the desired number of replicas. Next, selector with match labels determines which pods this deployment manages. In our case, we're targeting pods labeled with app Postgres.
Okay, so we're filtering by labels, then we have template, which seems to define the actual blueprint for the pods themselves.
Yes. Under template, we have metadata again, where we add the app. Postgres label to the pods created from this template. This ensures consistency with our selector.
Right, so the deployment manages pods that have this specific label. Makes sense. Now let's jump into spec under template, where things get really interesting.
Under containers. We define the specifics of our PostgreSQL container. We give it the name Postgres and specify the image postgres.14, which is the official PostgreSQL image from Docker Hub.
So we're pulling a pre-built PostgreSQL image, which is super convenient. But what if we want to use a different version or a custom image?
You can easily change the image tag to a different version like postgres.14 or replace it with the URL of your custom image hosted in a registry.
Flexibility is key. Next, we have ports, where we expose the PostgreSQL port 5432. That's the standard port for PostgreSQL, right?
Correct. This makes the port accessible within the cluster.
Then we have and from with config map ref. That looks familiar. We're referencing the config map we created earlier.
Exactly. This is how our PostgreSQL container gets its database settings, like the database name, username, and password from the Postgres config map.
Awesome. So everything is neatly connected. Now on to volume mounts. It seems like this is where we hook up our persistent storage.
Absolutely. We mount the persistent volume claim Postgres PVC that we created earlier, giving it the name Postgres data within the container.
And mount path specifies where this volume will be accessible inside the container.
Right. Varlib Postgres data is the standard data directory for Postgres.
Precisely. Finally, under volumes, we define the volume itself, giving it the name Postgres data and referencing our Postgres PVC.
So we've linked everything together, the deployment, the container, the config map, and the persistent volume claim. It's like assembling a high-tech Lego set.
A great analogy. Now, how do we actually deploy this masterpiece to our Kubernetes cluster?
Well, based on what we've done so far, I'd say we use the trusty kubectl apply -is postgres -deployment.yaml command.
Well, you're absolutely right. And just like that,
Yeah.
your PostgreSQL database will spring to life in your Kubernetes cluster.
This is amazing. We've successfully deployed a fully functional PostgreSQL database, configured it, and ensured that its data is safe and sound. But how do we actually connect to it? That's got to be the next step.
Yep.
You got it. We need a way for our applications, and even for us, to communicate with our PostgreSQL database. That's where Kubernetes services come into play. But let's take a breather and dive into that in the next part of our deep dive.
It sounds like a plan. We've covered a lot of ground already, from defining deployments to linking everything together with config maps and persistent volume claims. I can't wait to see how we bridge the connection to our PostgreSQL database in the final part of our deep dive. Stay tuned. All right, we've got our PostgreSQL database up and running in our Kubernetes cluster, neatly configured and connected to persistent storage. Now, the burning question is, how do we actually access this database?
That's where Kubernetes services step in. They act as a bridge, allowing other applications, or even you directly, to communicate with your PostgreSQL database without needing to know the specific pod IP addresses, which can change dynamically.
It's like a phone directory for our Kubernetes cluster. We just look up the service name, and Kubernetes takes care of routing our requests to the right destination.
Exactly. And just like with everything else in Kubernetes, we define services using a YAML file.
Okay, I'm sensing a pattern here. YAML files are the bread and butter of Kubernetes configurations.
Yeah.
So what would a service YAML file for our PostgreSQL database look like?
Let's call it postgres-service.yaml. Here's a basic example. YAML service.name postgres-service.type node port.ports.port 5432 target port 5432.node port 30,000.selector.app.postgres.
All right, we have appy version.kind and metadata with a name, just like before. Then in spec, we have type node port. What does that mean exactly?
Node port is a type of service that exposes the service on a static port on each node's IP address. It's a simple way to make the service accessible from outside the cluster.
So if I have a Kubernetes cluster with 3 nodes and I deploy this service, I'll be able to access my PostgreSQL database on port 30,000 of any of those nodes' IP addresses.
Precisely. Now, under ports, we define the port mappings. We map port 5432 on the service, which is the standard PostgreSQL port, to port 5432 on the target pods.
And node port. 30,000 is the port on the node's IP address that we'll use to access the service externally.
Exactly. Finally, selector with app Postgres ensures that this service targets the pods belonging to our PostgreSQL deployment.
So it's all linked together beautifully. We create the service using kubectl apply-f postgres-service.yam, and now we can connect to our database externally. But how do we actually do that? What's the command?
You can use the PSQL command line tool to connect to your PostgreSQL database. If your node's IP address is, just say, 192.168.1.100, you would use the following command. PSQL-192.168.10.000-u myuser-myd-mydb.
So we specify the host IP, the node port, the username, and the database name. Straightforward enough. But what if I want to connect to the database from within the cluster, from another pod? for instance?
In that case, you can simply use the service name Postgres service as the host name and the service port 5432. Kubernetes will handle the internal routing for you.
That's incredibly convenient. Now, suppose our application becomes super popular and we need to scale up our database. Can we do that easily with Kubernetes?
Absolutely. Scaling is a breeze with Kubernetes. You can simply use the kubectl scale command to adjust the number of replicas in your PostgreSQL deployment. For example, to scale up to 3 replicas, you would use kubectl scale deployment, Postgres deployment replicas 3.
Kubernetes will then magically create 2 more pods running our PostgreSQL database,
Awesome.
ensuring high availability and better performance.
That's right. And if you need to scale down later, just adjust the replica count accordingly.
Wow. Kubernetes really simplifies the complexities of managing a database. But what about backups? Data safety is paramount, especially for a database. How do we handle that in Kubernetes?
There are various approaches to backing up your PostgreSQL database in Kubernetes. One common method is to use the pgdump tool to create a backup file. You can execute this command within a pod using kubectl exec.
So we can run a command like pgdump myuser -d myd backup.sql to create a backup file called backup.sql.
Exactly. Then you can copy this file to a persistent storage location or even outside the cluster for safekeeping.
And for restoring,
Yeah,
we can use PostgreSQL with the ONTAT option to specify the backup file.
that's right. Kubernetes provides the flexibility to implement your preferred backup and restore strategy.
This has been an incredibly insightful journey into the world of PostgreSQL and Kubernetes. We started with config maps for managing settings, then moved on to persistent volumes and persistent volume claims for data persistence. We deployed PostgreSQL using deployment, exposed it using a service, and even learned how to scale and back up our database.
It's remarkable how Kubernetes simplifies the deployment and management of complex applications like PostgreSQL, making it accessible even for developers who aren't Kubernetes experts.
Indeed. And the beauty of Kubernetes is that it's constantly evolving, with new features and best practices emerging all the time. There's always something new to learn and explore.
Absolutely. So I encourage everyone to dive deeper into the world of Kubernetes, experiment.learn, and don't be afraid to ask questions. The Kubernetes community is incredibly supportive and always willing to help.
And remember, this deep dive was just a starting point. There's a whole universe of possibilities waiting to be discovered in the world of Kubernetes. So go forth, explore, and build amazing things.
Happy coding.